Hi, everybody. Welcome back to an episode on thermal measurement. In this episode, we will dig deeper into how to measure temperatures and not only on surfaces but on really small spots. So, at the end of this episode, Eike, my guest, will tell about how he has developed a method to be able to control the process of laser 3D printing, measuring the actual temperature on the spot during the process. It's a spot size about 200 micron. If you can copy that, you're pretty smart. But if you see this entire episode, you will learn a lot about how to do that. So please follow.
Hi, Eike.
Hello, Peter.
Thank you for joining the podcast Everyday Metallurgy.
I am glad to be here.
Yeah, Eike, you are one of the few who did come here voluntarily because you watched a previous episode on laser forming where I was crying about difficulties in measuring temperature. I thought initially that measuring temperature was the easiest thing in the world. You do that every day in your bath or at the hospital. But when you go industrially and you go to higher temperature, suddenly things like emissivity, hot spots, perfect dark spots, words that I've never heard before came flying in. But you contacted me because you had the solution.
I have the solution of everything. No, I'm
Yes.
joking, but yes, indeed, the temperature measurement can be difficult.
Yeah, so therefore today we're going to make an episode on how to measure temperature using pyrometer technology. But before we dig into it, will you give a short introduction to yourself, your background, where you're from, and what you do on your daily life?
Yes, I like so. I am Eike Boback from Germany. I'm working at Sensortherm, a company based near Frankfurt. And we are a distributor and developer and manufacturer of pyrometers, so infrared thermal measurement. And I am here quite random. I studied mechatronics and worked in robotics. So my background actually robotics and the automation industry. Learned here in Germany at ABB Robotics. I think the most of you will know ABB.
Yep. Yeah.
And yeah, then I came quite randomly to the measurement technology, and I'm loving it.
Great. So what is this pyrometer technology? What is it about?
Yeah, pyrometer technology is a quite simple method because some random guy 100 years ago, Mr. Planck, physicist,
that guy,
you may know him, discovered everything is emitting energy, and this emitting energy is in our world with our temperatures in the infrared spectrum. So our method is now measuring this emitting energy, this infrared light, to get the temperatures of these surfaces, materials, which emitting these energies.
Yeah.
Right.
I have one of these guns you can point on your house and see if the isolation is bad. But very often when I point at it from one side and then I go to the other side, I have two different values. if I point on a rough surface and a smooth surface, I get different values. What is going on? Is it did I buy it too cheap?
Yes and no. So every surface is emitting energy, but it also reflects energy, like sunlight and other heat sources in your environment, and it can absorb energy from also the same sources. And maybe I show you some simple picture describing the principle.
Yeah.
You can see.
Yeah, it's perfect.
All radiation absorption and emission and reflection of a real object. So if you're measuring from one side to it, you may have other emissivity, some reflection and some transmission, mostly not on solid normal surfaces, but also. So if you measure with the wrong tools, you get wrong measurements. So I will go back.
Yeah.
Every pyrometer, your thermal measurement tool, whatever you are buying, normally in a shop you can go to, you get 8 to 14 micrometer sensitive pyrometers. So you are not in the super short wavelength where you can get better measurements. But as I noticed, as I said, Planck found some interesting curves and emissivity and so on. So there's one part what he get from it. So the intensity of the light gets stronger if on the short wavelength if the temperature rises. So on your house you normally don't have over 100 degrees C, so there's not much light, not much energy you could measure. So you have to use these 8 to 14 micrometer pyrometers and don't get the best results.
Okay. But then if I go to my lab, I am today working with high temperature applications. So I'm working on electrification of high temperature applications. And typically I have temperatures between 800 and 1200 degrees. Today I'm measuring with a thermocouple. But the thermocouple was making tricks on me, because I thought I was measuring the gas, but it was measuring the radiation from the heating element instead. So I had to make an angle of my system to place my thermocouple away from the radiation site.
Right.
Yeah. So could you also use your pyrometer technology at these temperatures, and how does that differentiate from the low temperatures?
Actually, it will get easier. Everything hotter is emitting more light, more energy, so we have more to detect. And I like everything above 500 degrees C. So there it can start to go quite short wavelength infrared, and then I have the least effects on reflections and so on. So yes, everything above 500 degrees C is good for us.
Yeah. But then in the episode I talked about this with the laser forming. Anders Thompson, who made the trials at the university, told that he used a laser pyrometer to measure temperature on the spot of the laser well. And he was measuring around 900, 1000 degrees, but suddenly the steel melted. It was a stainless steel with a melting point above 1400.
Yes.
So he was so confused. I'm measuring 900 and it's melting. So he was 500 degrees off. Is that the trustworthiness of the pyrometer?
Yeah, it's sometimes trial and error because you have to get the right parameters in the pyrometer because I told you the emissivity is not constant. So on steel, like shining bright, you see really much reflection. And if in the visual lights you can see the reflection is high, it's a high chance in infrared it is too. So you have to put on highly reflective materials the emissivity quite low. And so it's a factor, and it sounds like a real thing that the pyrometer could say 800 degrees C and it's 1200 or whatever.
So often when you start using it, how do you ensure that you measure the right thing? I have a surface here, and how can I calibrate that I'm measuring the right thing then?
Yet you introduced your friend or colleague with the melting point. So normally you have a material, you know the melting point of it. So if you're allowed to do over the melting point, you can rise the temperature slowly up to the melting point. And in the melting point, you know that exact temperature. With pyrometer, you can then adjust in the melting point the emissivity and know exactly the absolute temperatures. Yeah, that's one method.
But then you have 1 point. So how do you know that the slope is right?
Yeah, it's difficult. So you have to know the emissivity for the melting, for the melted material. Normally, it will not change over the process in the melted point, but then on different temperatures, you're right, it can change. And then you only have a relative value you can work with.
Yeah. So this, I have heard people talking about calibrating in, is it called dark black?
Yeah, or it's dark black or black hole, black source, heat calibration source, whatever you call it. In the physics, it's called black body, describing a body which has an emissivity of 100%, like perfectly giving you 100% of the energy of the surface.
Okay, so that is the 1 point down here, and then you have the melting point, and then you can make a linear.
Oh yeah, not that much. I can show you what I mean.
Yes,
this is only the calibration of the curve of the heat curve. 1 moment.
Yeah,
and to calibrate. Now you could see the thing. This is like the heat source I mentioned.
Yeah.
If you look inside it, you have nearly 100%. It's not possible exactly 100%, but nearly. So that's the point where you can calibrate the pyrometer over this Planck curve, it's called.
Okay.
And then you only adjust it with the emissivity factor you can put in the pyrometer.
Aha.
Yes.
But then where can you use it? How big a spot do you need?
No, the spot size is a complete different thing. So you can use spot sizes from 0.4 millimeters So very small up to whatever you want, nearly.
Yeah.
You also could use fisheye lenses or whatever.
Okay. So I have some friends working on laser deposition of metal powder, and they often talk about they want to be in control with the temperature during the process. Is that possible?
That is perfectly possible. So right now we're working on new devices exactly for this process. This is one of the most challenging processes for us, because we have first the slow melting point you mentioned.
Yeah.
So sometimes it's only laser spot like 100 micrometers big in size, and so the melting bath is bigger, but like 200 micrometers in the process. And then on the second point, you have very, very fast speeds, scan speeds of this process. So they go with this small spot up to 1000 millimeters per second, so 1 meter per second, and that's super fast. So we have to measure very, very fast. So we have this overlap of this coming measurement points next to get the best measurement. And the next step, if you can measure it, you can control it. So we can go to the closed loop and say, now the temperature is constant, and take this laser power to get this constant temperature.
Yeah. So have you tried to adjust it on the run? Because I could imagine first layer, you have a cold substrate. It's difficult to you just need to put in power. But then on your second and your third and your fourth, you might increase temperature of the substrate, and then you should reduce the power input on your laser. Is that the way you control it?
Yes. So actually, you have to control it even on the first layer, because in the corners the energy varies too, and sometimes you are slower because of the mirrors of the scanners have to move too. So it's not constant energy in the surface you want to create. So actually, I have an example of energy deposition, not of LPBF, but I can show you this. And many of the users know some errors coming from not constant temperatures. So as I mentioned on this curves, you also have on LPBF. There are many effects on the material, which is not good for perfect printing, for welding, whatever you want. And you see very big differences in the temperature, up to 100 degrees up and down and up.
Whoa.
And this is effect also gives you bad structure in the material. So like some holes and so on. And our approach is to control the laser power you can see here in green on the right side, and get a constant temperature, and the effects on the material are gone. Right.
That's pretty smart. And you can control it down to 200 microns in spot size, you said?
Yeah. So it's only depends on. I will go back. It only depends on the spot size and the speed you go. So if you have a big spot size, you don't the speed can go faster, and on the other way, if the speed is slower, we have less speed, we can go smaller spot sizes. Yeah.
Eike, then I have a problem sometimes.
Yeah.
That the steel that I am working on, it creates an oxide film when it gets hot. So my surface changed from when it's virgin material, it's shiny, stainless colored. But after a few hundred hours, it gets dark and rough and no shining back. How much does that influence on the measurements? Do you have a feeling on, are we talking several hundred degrees that it will vary due to the different surfaces, and what could you do to calibrate and stay within the right measurement?
Yeah, you're right. Oxidations are quite a problem sometimes not. So if we're talking about very, very bright steel or copper, aluminum, there is a problem if the emissivity changes with like oxidations. Because if we go from emissivity factor from 5% up to 20, we are doubling it 2 times. So the factor is quite high. Yeah. But if you go from 80% emissivity from a quite rough surface to 90 to even rougher surface, the influence is quite low. So this is the first. Also, you can use some tricks. I have one trick right here. So we are working not with a normal pyrometer. We are working with a ratio pyrometer, 2-color pyrometer. There are different names for it. So we have the pyrometer. You can see the inside. And there you have one detector, and there you have the second. So we're measuring with 2 different wavelengths, beam splitting it with a dichroic mirror. And then we get different wavelengths, measuring both at the same time. Yeah. And measuring not the radiation we get, the emissivity, but the difference in the emissivity at this wavelength. And then you get a whole new value, less sensitive on variations in the emissivity. So there you can buffer a bit of the effects, but not the whole process. So some adjustment has to be done too.
Okay. Then I have a process where I have my high temperature inside a chamber with an active gas. So it's not open, but I can put a glass so I can look through. Is this measurement method, can I measure from outside through a glass into the system?
Yes, it can. You have to know your glass and choose your glass. The more important method, because some glasses are more transmittive in this infrared than others. So I can tell you up to 2.6 micrometers in wavelength. You can use like the normal borosilicate and sapphire. These are the common glasses for this application.
Sounds expensive.
It sounds expensive, but the normal glasses are quite good for it.
Okay. But can they stand? Because I have some quite heavy radiation. So the temperature on my surface is above 1,000 degrees. So the glass will also see quite a lot of heat on the inner side. Can these glasses survive that?
On these cases, I normally see like water flange systems where you have 2 glasses and between it there's some cooling water cooling the glasses. So on different reactors on semiconductor industry where you have over a very long time, very high temperatures, this is the normal use case. Yeah.
Okay. Interesting. Where else are these pyrometers used? I've only been thinking in my own world of high temperature heating element and the laser deposition in 3D printing technology, but where else are they used out in the world?
So everywhere you can't use a thermocouple, because I mean, thermocouple is first thing to measure every temperature if you can, but you have in the world quite many processes you can't use them. So laser is a perfect example, because laser have so small spots or super high speeds, it's not possible. A different application is the induction heating, because induction normally uses, not normally every time, electromagnetic fields. And the thermocouple is also from steel, maybe other metals, whatever, platinum. And it also heats from electromagnetic, whatever, you know what I mean.
Yes.
Electromagnetic fields.
Yeah, of course, you induce current in it.
Errors in the measurement from the fields. There are errors on the material, because the thermocouple also get the heat from the material, from the surface itself. So on the low temperatures, it can show you complete false values.
Yeah, I can recognize that in what some of the measurements I've seen.
Maybe a different question: why don't you use the thermocouple for your house, measuring your walls?
It's very difficult to get contact.
Right. So that's the next point. If you have moving parts, it's not quite easy to get these, and so the optical way is sometimes more accessible.
So do you see any future potentials of this? Are there new applications, new methods that we haven't seen yet?
Oh yeah, there are many. I mean, the topic of laser is quite new too, but there we go further, and we're doing melt bath measurements in size too. So with the ratio pyrometer, you can measure the melt pool size too. So what we are doing with cameras in welding technology. In future, we want to make these with less complex pyrometers and get rid of expensive camera solutions.
So the size of the melt pool.
Yes, right. We have value in our pyrometer, the signal strength. So if we calibrate a melt pool size, you can say this is 100%, and then these 100% are a value of size like 2 millimeters or whatever you type in, and then you have the melt pool size combined with the signal strength, and then could control to the melt pool size if you want to.
That's smart. So welding will be next step.
Yeah, so welding is always very, very important to get the right temperatures and the right values in the process.
We also slightly talked about some other things that your company does. Other ways of measuring using radiation. Can you give a short insight in these, or should we leave them for another episode?
I can talk about a little bit. I mean, you want to hear something about the spectroscopy?
Yes, I do. Yeah.
Yeah, spectroscopy is very, very interesting. So we are in the Dynamic group, have some companies in it are experts in spectroscopy. And this is like a pyrometer, but using different wavelengths in different spectrums and analyze the whole spectrum and not only like one small wavelength spectrum. So there you can analyze quite interesting data. It's used like to analyze in clean tech and green tech, where you can define the ingredients of gases, materials, and also your food. We can use this value for quality control and so on. This is super interesting.
Yeah.
Because also, like you mentioned, the oxidation on your surface, you would recognize it through spectroscopy. So in a perfect application, you could use a pyrometer, next to it the spectrometer, and look for the oxidations and then adjust the pyrometer to the oxidations.
Is it like optical emission spectroscopy? Is that the way it works?
Yeah. So it's also emission you detect with the spectrometer, but also you could use defined light if you have a light source, beaming, looking through a to a surface.
Yeah.
And then get everything reflecting from the surface and detecting this. There are different methods. Yeah.
Wow. Thank you. I would like to stop here, but before we end, could you give some insight in, if people are curious to learn more, where could they go?
If you want to learn more about pyrometers or what you're trying, okay.
Yeah.
I mean, the technology is not the newest, but the innovations are quite small but big in the process. So everything you want to learn about pyrometers, I would recommend our academic partners. So look to for example, BIAS in Bremen, Germany, using our pyrometers for quite interesting research. Also Aalen University in Germany. These are quite interesting works they do.
Okay. Perfect. Thank you very much.
Thank you.
And are people allowed to reach out to you directly if they want
to? Of course. I like if they do it.
Perfect. I'll put your contact data in the comments under the YouTube episode.
Perfect.
Yeah. So wonderful. Thank you very much. I learned a lot.
Thank you very much.